So last time we finished with this beautiful red triangle, and we passed the transformation matrix through the uniform buffers. But what we still do is hardcode the vertex coordinates in the shader, and this is something that we're gonna change. We want to pass them, of course, from the CPU, and for that we need to use vertex attributes and vertex buffer to pass the data to the shader. So let's start with the shader. How it's done is simply we say, okay, this position is now actually an input vector 3, because we don't really, I mean, we can pass vector 4s as well, but logically we are having just 3D coordinates, so we can do that. And we want to specify a layout with a location identifier for this vertex attribute. So this is just first attribute with a location identifier 0. And we want to remove all this stuff because now we're going to be passing this as a vertex attribute. And since this is vector 3, but this is vector 4, and the matrix multiplication works with vector 4, we want to convert it to vector 4 like this by specifying 1 as a W. So this is a good change for the shader, so that compiles and kind of works. But now we of course get the problems here in our validation, in our pipeline. And let's see what we need to do to make this work. So we need to describe vertex attributes. Oh my god, there's a lot of T's. Attributes and vertex buffers in the pipeline. Then we want to create vertex data. We want to create vertex buffer. We want to upload vertex data. Oh my god, vertex data to the vertex buffer. And then when we draw, we want to bind vertex buffer to the draw call. So yes, this one, let's start with that. So we want to tell the graphics pipeline that we actually have the vertex buffer, and we want to specify how to interpret it. So basically the layout. And this is specified in this vertex input state. So this is the input state for the vertex shader, basically. And this is a pretty simple structure. It has basically two parts, right? 4 fields. The vertex buffer description and the vertex attribute description. So the vertex buffer is basically how many buffers do we want to supply of data, and we want to specify only one buffer for now with just position. So we're gonna specify num vertex buffers just 1, and vertex buffer descriptions we can just inline it like this, a pointer to SDL GPU vertex buffer description. And this is a structure, so basically the slot, we can have multiple vertex buffers and they take slots. So the slot number 0, because we have just one. We can also omit this if we want, but let's be explicit here. Then the pitch is basically a number of bytes in this buffer of data between each vertex, let's say, right? If we want to advance from one vertex to another, we need to step this number of bytes to start reading the data for the next vertex. So this is the pitch. So we say pitch, and this is some number that we're gonna talk about in a bit. Then this input rate is basically whether this is a vertex buffer or an instance buffer, as far as I understand. This is something that we really don't care for now. We can leave it as is actually, because this would be the default value for the input rate. So the pitch, let's maybe quickly go to this one, to the creation of vertex data. So let's say we want to draw still a triangle. The triangle consists of, well, 3 vertices, right? And each vertex needs a vector 3 of position. So let's do exactly that. Let's say we have maybe a data type of vec3 of 3 floats, so vec3, that's fine. And now we specify vertices, which would be just a slice of vec3, and that would contain 3 elements, let's say -0.5, minus 0.5, so x, y, and z, and yes, just z. And then we have the center top, right? So like this. Whoops. Let's have a center top like this, and then bottom right like this, right? So this is the same coordinates as we used before in our hard-coded version, but now we specify it here. So the pitch between each vertex, so the step in bytes, is basically one element of our vertices slice, and this is vec3 exactly, right? So what we can do is just specify size of vec3, and this would be our pitch from the vertex buffer. Now the next thing that we want to do is specify the vertex attributes. So let's maybe define an array for that, or rather a slice for that. So vertex attrs or something, and that would be just a slice of SDL GPU vertex attribute, which is this little structure, and it's actually pretty simple. So what it defines is from which buffer to get it, so that would be 0. We can also omit this because we have just one vertex buffer. Then the location, and this corresponds to our shader location, this one, so location would be 0 for the attribute that we are describing, which is of course the position, which is the only attribute we have. And the important part here is also format, which is float3, because float3 here, as you can see, and vec3 is also 3 floats. And offset from the buffer, that would be 0. We can omit this for this very simple example, but we will need it later when we add more attributes, so let's keep it explicit. Let's say offset 0. So, and yes, this is of course just one element. And now we can specify it here in our pipeline. So we have the vertex buffer description, and now we need to specify the vertex attributes, and that is the same format, more or less. Num-vertex attributes is, well, we can just say len of vertex attrs that we described here, and vertex attributes themselves are just a pointer to the raw data of vertex attributes. And yes, this needs to be casted to U32 because that's the SDL API. It doesn't get the int, but rather U32. So with this, we basically described in our pipeline that we have one vertex buffer that is of this structure. So for every vertex, we read this amount of data, the pitch, and we interpret them like this. Basically just one vertex attribute at location 0 with format of float3. This is all in good, and let's take a look at what we've done. So we created vertex data, we described vertex data in the pipeline, but we didn't do this, right? We need to create a vertex buffer, and we need to bind it, and we need to also upload the vertex data here. So like if we run the game right now, it will still complain a lot about mostly the fact that the vertex buffer is not bound. Like here, for example, right? We say vertex binding is null, right? Because we never did this. So creating a vertex buffer is actually pretty simple. We say vertex buff equals SDL create GPU buffer. We pass the GPU device to it, and as usual the create information, right? And this create information is how we use it and the size and usage for us, because we are just using this as a vertex buffer, not index or any of the compute stuff. We just say, yeah, the usage is only the vertex. This is a hint for the graphics driver. And the size is a byte size of vertices. So let's maybe have a variable for that because we will need it more. So let's say vertices byte size. That would be length of our vertices. Of course, multiplied by size of element of vertices. So this we can, how we can do this with just a first element, right? And byte size can be this, and this needs to be casted to U32 because this is what SDL expects. And now we have our buffer of the same size as vertices, and we've done this kind of. And we also can quickly do this binding for the drawing. So when we want to issue the draw calls like this, we want to bind the vertex buffer so the pipeline knows actually from which exact data region to read the vertex attributes for the shader to draw. So let's say bind vertex buffer. We want to bind it to the surrender pass, and starting from the first slot, which would be 0 because we only have one buffer slot, which is 0 for one binding, and we specify one binding with just one binding. And here we can as well just inline our structure like SDL GPU buffer binding. And this GPU buffer binding is a simple structure. It takes a buffer which we want to bind and the offset, like where to start reading. We want to start reading from the beginning, so we say buffer equals vertex buffer that we just created, this one, right? And the offset we can maybe omit because this is more advanced usage. We don't really care for now. Now we can see that there are no errors as far as Vulkan is concerned, because we bind the buffer, everything is set up properly. The problem is that the buffer is completely empty. We never upload the data for it. Yes, so uploading data into the GPU buffer is actually a bit involved. So let's describe what we need to do. We need to create a transfer buffer, which is basically just some memory on the GPU side that is used for transferring data from CPU, from the normal memory to GPU. Then we need to map the buffer to like normal memory so we can copy it. So map transfer buffer mem and copy from CPU. Let's call it like this. This would be our transfer buffer. And after that we need to begin a copy pass and then invoke upload commands. The upload commands is something that will basically just copy data from our transfer buffer to real buffers. In our case, this is just one buffer of vertex buffer, right? And then we want to basically end the copy pass and submit. So this is the process, and let's just write some code for that. So first we need to create the transfer buffer. Transfer buff is SDL create transfer buffer. We pass the GPU, and then of course again the create info, which is just a descriptor, meaning how the transfer buffer is used. We can upload or download. We want to upload, so we specify usage upload, and the size of the transfer buffer. So let's say usage is upload, and the size, well, we want to upload just the vertices, but theoretically we could upload also the indices or even textures in one go. So this size can be more than the vertex buffer that we have. This is also can be reused. So basically this is just some amount of memory on the GPU side that we want to use for transferring data from normal memory. Yes, for now we're gonna say it's this byte size. Also needs to be U32, right? And this is done. Now we want to map the memory, so we can actually just copy it from this slice into GPU memory, and this is done with SDL map GPU transfer buffer. We specify the device, then the buffer, and then the cycle is something that is actually described here, a note on cycling, and it says that you see all the functions and structs that involve the writing to a resource have this cycle bool, and basically this is hiding some complexity in Vulkan, for example, when you would need to properly synchronize writing and binding of buffers, so you don't end up breaking stuff, right? So this basically they all function as ring buffers. So if the resource is bound, then this transfer buffer will be actually a different amount of memory that is not currently bound. So this is done for that. We don't really care about this right now because we are only uploading once, and we are doing this before actually binding, before the drawing. So we can just specify cycle false for now, and yes, that returns us a pointer to the memory. So this would be transfer mem. You see, this is just a raw pointer, and with this pointer we can do the very simple thing that, like the easiest thing that we can do is simply say mem copy, and now we want a copy to the transfer mem, so this one from source, this will be a row pointer to the vertices data, and the size is of course a size in bytes, that would be vertices byte size. So at this point we have transfer data field with our vertices, and we need to unbind, or rather unmap, the transfer buffer, so GPU transfer buff, so it knows that we are done with copying. And at this point the memory is supposed to be on the GPU side, so this is done. And now we need to invoke some commands for the GPU to actually copy this data from the transfer buffer into the buffer that we want to use for rendering, so the vertex buffer in our case, right? And for that we need to acquire another command buffer, just like we do for rendering, so we can just even copy paste like this, no problem here. So we do the, let's call it copy command buffer, acquire GPU command buffer, and to actually make stuff happen we need to submit the command buffer, so we can also copy this like this. This would be our region where we would invoke commands. And to actually do the copying we say copy pass. To create the copy pass we say SDL begin copy pass, and we attach it to this command buffer, so it's related to that, right? Copy command buffer. And just like with the render pass, we want to end the copy pass, so we say SDL end render pass and GPU render pass, and this is all done. And the only thing that we really need to do is actually invoke the commands to transfer the data from the transfer buffer to the real buffer. And with that we can say SDL upload to GPU buffer in this copy pass, and then it needs a source, destination, and the same cycle boolean here. So we say source, destination, and cycle would be false because we don't care for now. Yeah, I'm sorry, that's of course not the render pass, but and copy pass, that's a beauty of autocomplete. And just like let's take a look at what this needs to have. So the first element is of course the transfer buffer location. This basically specifies like from which transfer buffer and from which place in this transfer buffer we want to copy. So that would be transfer buffer, our transfer buff, and the offset is 0 because we are copying from the very beginning. And then the second argument is GPU buffer region, you see, and this is basically the region where we want to copy into from the transfer buffer, and that would be of course our vertex buffer. And the offset is also 0 because we are copying to the beginning of the buffer, but we need to specify the size, like how many bytes do we want to copy, and that would be again our vertex byte size. Vertex byte size, and that of course needs to be a U32. So now I think this should work. You see, this works as it was before. The difference is now that the shader does not hardcode the positions, right? We just pass it from the actual program, and we can change it, like, I don't know, let's say the pointy part should be very high and we have got a taller triangle. So this gives us of course much more control. Let's maybe take a look at what we've done so far. So we defined a data type for vector3, we defined a number of vector3 to draw a triangle, so 3 vector3 in a slice. We calculated the size, then we created a vertex buffer, then we created a vertex buffer of this size, then we created a transfer buffer of this size, then we mapped the memory for the transfer buffer and copy the vertices data to this transfer buffer. Then we acquired the command buffer to invoke some uploading commands to the GPU. Then we begin a copy pass to start copying. We invoked some actual uploading commands that would copy from the transfer buffer into the GPU buffer that we use as a vertex buffer. We end the copy pass, and finally we submit the commands. And for the rendering, we specified that the pipeline uses one vertex buffer with this pitch, so how many bytes to advance for each vertex, and every entry in that vertex buffer basically has these attributes. It describes these attributes, which is just one attribute for now, which is a vector3, or rather float 3 at location 0. And finally, to really make use of that, we binned the GPU vertex buffer like this here. And one thing that we could do as well is that because we are just uploading once and never care at all, we should probably release the transfer buffer once we've done. So let's say SDL release GPU transfer buffer from this device. And yeah, you see it still works. And we can do something more interesting. For example, let's change the colors. And for that, what we need to do is specify another input attribute. So let's say that would be vector4 of color. The locations should be, of course, the next one. That would be 1. And the vertex attribute needs to pass it to the shader attributes, and the value will be, of course, interpolated between vertices and mixed together. So for that to work, we need to specify an out vector4 attribute, and the location for the out we can start from the 0 again, because it's the first out attribute. And we can see, as simple as that, we can just pass it to the fragment shader. And now in the fragment shader, we are using kind of the same stuff. So we have the out color. Let's rename it to frag color to avoid some name collisions. And basically what it does is it takes an input attribute of name color of the same type, right, vector4, and the location 0. So this needs to be the same. And now we can just specify it here. So the shaders are now expecting 2 vertex attributes, and they should pass one to another. Let's see if that at least compiles. Yes, it does, but of course the triangle is black because we never really specified any colors at all. So because we changed the expected attributes by the shader, we need to specify them here in the pipeline definition, right? And this is where shader reflection would come in handy, but since we are not using any of that, we're specifying everything by hand. So we need to specify another attribute here as well, and that has to be mirroring the structure here. So that would be float4 at location 1, and the offset is actually interesting, right? This actually depends on the data layout and our vertex buffer, because the first position we read from the 0, but the color must be read from some other place, and in our case that would be right after the first attribute, right? So this offset should be basically the size of float3. But to not get confusing, a good practice is to just define it as a proper data structure. Let's say vertex data. Let's say that our vertex contains a position of vector3 and not just being vector3, and the color, which would be, well, it could be just for f32, which would be a vector4, but actually SDL has a nice type of f color, which is exactly for floats. And now we can say that our vertices are actually not just vec3, but actually structures of position and color, right? And the color could be just a usual one, like, so the first would be red, then green, and then blue, right? So let's take a look at what else do we need to change. So we changed the structure of our vertices, so each vertex now contains position and color, exactly like the shader expects. And the size is fine because we specifying the first element, which would be this one, so this is the size of vertex data. All the size that we use here is fine, all the sizes should scale properly. We specified the vertex attribute for the pipeline, and yes, one thing that we need to do is specify the offsets. So the position, the first one, should be an offset of 0, but to not hard code that, we should probably use a Odin offset off built-in procedure which you can pass a type from which to offset, to calculate the offset from, and the field. So that would be position, and that must be, of course, u32, you guessed it. And for the color, it needs to be, of course, offset of color. So this is also good because we can actually see, okay, this is position, this is color, and we can also reorder now stuff in the structure, and this will all still work because the positions, the offset will be recalculated correctly. And the final thing is this pitch, because when reading data for each vertex, the pipeline will still advance by this size of, which is still vec3, but instead of that, it of course should be the size of our whole vertex. And now, hopefully, this will give us a nice and colorful triangle, much better than before. And of course, it's all here. We can just change colors, we can do some different things. So this is basically now is our mesh with some game unit sizes and positions and colors defined on the code size rather than shader size, and the shader just takes it and draws it. So yeah, hopefully you get the idea on how it's done right now, and next time we're gonna try drawing quads instead of triangles, and quads consist of two triangles but they share vertices, so we are be doing indexed rendering, and we are gonna create another buffer, index buffer, and use the indexed rendering for that. So stay tuned.